Today we are going to study the second part of electrostatics. Now what is equal when you have that video which we had seen earlier when a glass rod or a plastic ruler is rubbed on silk? The amount of negative charge on the rod or plastic ruler is equal to the amount of negative charge on the silk cloth. For an isolated system, total charge is conserved. The total charge can neither be created nor destroyed. Like charges repel and unlike charges attract each other. By Millikan's oil drop experiment, it was found E is equal to 1.6 into 10 raised to minus 19 Coulomb. A glass rod, when it is rubbed with a silk, a charge of the order of 1 microcoulomb 10 raised to minus 6 appears on the glass rod. The number of charges can be found as the ratio of Q upon E, that is 6.25 into 10 raised to 12. The number of charges are so many. Rather than quantization of charge, a continuous variation of charge is seen. Well, let us see what is exactly quantization of charge. Q is the charge, N are the number of charges, total number of charges obviously will become N into Q. For electron, E is equal to 1.6 into 10 raised to minus 19 Coulomb is Q. Quantization implies discrete nature of charge. Integral number of charges are transferred from one body to another, but the magnitude of elementary electric charge is extremely small, so the discrete nature is not observed. So we have the conservation of charge. In physical process, charge may get transferred from one part of the system to another, yet the total charge in the system remains the same. For an isolated system, the total charge can neither be created nor be destroyed. Hence, there is conservation of charges. Force between the charges. Suppose we have a rubber which is negatively charged, glass is positively charged, they are unlike charges, so obviously there will be attraction. Now if you have negatively charged rubber with negatively charged rubber, there will be repulsion. So we have repulsion for the like charges. Similarly, glass and glass will obviously repel, so there is a repulsion here also. Coulomb's law is a fundamental law which governs the interaction between charges which are at rest, which we have already seen before. Now, if they are of opposite charges, negative and positive Q, there is attraction. If it is positive and positive, there is repulsion. And if it is negative and negative, again there is repulsion. The force is equal to Q1 Q2 upon 4 pi epsilon r square, that is in vacuum. For medium, it is Q1 Q2 upon 4 pi epsilon r square. If in medium, we can write in terms of K and epsilon naught. All this we have seen already. Epsilon permittivity of medium, epsilon naught permittivity of free space, K is the dielectric constant of the medium. We know F vacuum of F medium is epsilon upon epsilon naught. Relative permittivity or specific inductive capacity epsilon r is epsilon upon epsilon naught. Absolute permittivity of a medium upon permittivity of free space. That is F vacuum upon F medium. The material medium reduces the force between any two charges by a factor of epsilon r, the relative permittivity. Now how to find 1 upon 4 pi epsilon naught in our Coulomb's law? So we substitute the value of pi 3.142, epsilon naught 8.85 into 10 raised to minus 12 meter cube, kilogram raised to minus 3, s raised to 4, a raised to 2. So you get 1 upon 4 pi epsilon naught as 9 into 10 raised to 9 Newton meter square per Coulomb square. Now what is the definition of the unit of charge, that is Coulomb? You put Q1, Q2 as 1 Coulomb, R is 1 meter, and 1 upon 4 pi epsilon as 9 into 10 raised to 9 Newton meter square per Coulomb square. So you get F vacuum is Q1 Q2 upon 4 pi epsilon r square is 9 into 10 raised to 9 Newton. 1 Coulomb is defined as the amount of charge and placed at a distance of 1 meter from one another. Charge of the same magnitude in vacuum produces a force of 1 Newton. Units generally used are microcoulomb, nanocoulomb, and the picocoulomb. So we have now the two same type of charges, Q1 and Q2. Now the distance between them is r. So we put it in a coordinate system with O as the origin. Then R1 is the distance, R2 is the distance of Q2. So you have two forces F12 and F21. So obviously the force on charge Q1 due to Q2 is given by F12 is equal to Q1 Q2 upon 4 pi epsilon R1 minus R2 the whole square. So we put it in the vector form. The direction on F and Fr is same to be noted. So you get F12 vector is equal to Q1 Q2 upon 4 pi epsilon at R21 unit vector upon the mod of R21 square, since R mod is equal to R1 upon R mod. So you have similarly F21, the force due to the on charge Q2 due to Q1 is F21, that is Q1 Q2 upon 4 pi epsilon naught R12 unit vector upon modulus of R12 square. So R21 is equal to minus R12. Obviously F12 is equal to minus F21, or F21 is equal to minus F12. This will be true even if both charges are negative. Now Coulomb's law, when there are different types of charges, plus and minus, we put it in the origin again, the same thing has to be continued with that force on charge Q1 due to Q2 will be F12 is equal to Q1 Q2 upon 4 pi epsilon or R1 minus R2 square. So we put all the same things again. Direction of F and R are same. F12 vector is equal to Q1 Q2 upon 4 pi epsilon or R12 unit vector upon R12 mod square. Again the same thing. Similarly F21 force on charge Q2 due to Q1 is Q1 Q2 upon 4 pi epsilon R21 unit vector upon R21 mod square. R12 is equal to minus R21 again. F12 is equal to minus 21, or F21 is equal to minus F12. This is will be true even if both charges are interchanged. So that's all for today. Thank you.